Hello everyone, in this class we will learn about the relationships and operations of events. The learning objectives and tasks of this class are: the first is to understand the meaning of intersection and exclusion of random events. The second one can combine specific examples to perform intersection operations on random events. So, the key and difficult points of this lesson are the mutual exclusion and opposition of events, as well as the meaning of events. The difficulty lies in being able to perform intersection operations on random events and represent complex events with simple events. First, let's review the content we learned earlier. The first randomized experiment. The practice and observation of random phenomena are called random experiments, abbreviated as experiments, commonly represented by the letter E. So, the characteristics of random events. The first, repeatability, the second is predictability, and the third is randomness. The second knowledge point for review is sample points and sample space. Let's take a look at the sample points. Its definition is that we refer to every possible basic result of random experiment as a sample point, and we use lowercase letters omega to represent the sample point. So the set of all sample points in the sample space is called the sample space of experiment 1. We use capital letters omega to represent the sample space. Limited sample space. If a random experiment has n possible outcomes, such as omega 1, omega 2, and up to omega n, it is called a sample space. The capital letter omega set is a finite sample space. So, the elements in the uppercase omega set are the lowercase letters omega 1, omega 2, and all the way up to omega n. So, the letter representation is the set of uppercase omega letters. The third knowledge point for review is the definition of three types of events. Events that may or may not occur under certain conditions are called random events. An event that must occur under certain conditions is called an inevitable event. An event that is impossible to occur under certain conditions is called an impossible event. Let's use another language to express these three events. First, let's look at random events. We refer to a subset of the omega sample space as the random events of E, abbreviated as events, and refer to events that only contain one sample point as fundamental events. Random events are generally represented by uppercase letters such as A, B, C. In each experiment, event A occurs only when a certain sample point appears. An inevitable event, as a subset of itself, omega contains all sample points. In each experiment, there is always one sample point that occurs, so omega always occurs. We call omega an inevitable event. It is impossible that an event empty set does not contain any sample points and does not occur in each experiment. We call it an empty set, but I cannot achieve it. Okay, let's learn new knowledge below. We know that when several sets are finite sets, we need to find the number of elements in set A that are equal to the number of elements in set B that intersect with A. Commonly used enumeration method to list the elements in a collection. The number of elements in a crossing B is the number of common elements in the set A and B. When A intersects B and equals an empty set, the number of elements in A and B is the sum of the number of elements in the two sets. When A intersects B and is not equal to an empty set, the number of elements in A and B is the sum of the number of elements in A and B minus the number of elements in A intersecting B. From the previous learning, it can be seen that we can define many random events in a random experiment, some of which are simple and some are complex. We hope to infer the probability of complex events from the probability of simple events, so we need to study the relationship and operation between events. Let's take an example. In the experiment of throwing a dice, observing the number of points the dice face upwards can define many random events. For example, C equals the number of points I equals 1, 2, 3, 4, 5, 6. D1 equals the number of points not greater than 3. D2 equals the number of points greater than 3. E1 is equal to the number of points 1 or 2. E2 is equal to the number of points 2 or 3. F is equal to the number of points even, and G is equal to the number of points odd. So, please represent these events in the form of sets. Can you discover the connections between these events through the relationships and operations between sets? In fact, using subsets of the sample space to represent events allows us to use the knowledge of sets to study random events, providing an effective and convenient method for studying the properties and calculations of probabilities. Below, we will proceed with our research following this approach. Firstly, we write the above events in the form of a set, resulting in the following set. The set C1 is composed of the element 1, while the set C2 is composed of the element 2. The set C3 is composed of the element 3. C4 is a set composed of the element 4, while C5 is a set composed of the element 5. C6 is a set composed of the element 6. D1 is equal to a set of elements consisting of 1, 2, and 3 if the number of points is not greater than 3. D2 is equal to the set consisting of elements 4, 5, and 6, where the number of points is greater than 3. E1 is equal to a set consisting of elements 1 and 2, where the number of points is either 1 or 2. E2 is equal to a set consisting of 2 elements, 2 and 3, if the number of points is 2 or 3. If F is equal to an even number of points, then it is a set composed of 3 elements, 2, 4, and 6. If G is equal to an odd number of points, then it is a set composed of 3 elements, 1, 3, and 5. We use the relationships and operations between sets, as well as the relevant definitions of events, to discover that there are wonderful connections between these events, which can be divided into the following situations. First, represented in the form of a set, event C1 equals point 1 and event G equals point odd. They are respectively, C1 is a set composed of the element 1 and G is a set composed of the elements 1, 3, and 5. Obviously, if event C1 occurs, then event G must occur. The relationship between events is represented in the form of a set, where set 1 is included in sets 1, 3, and 5, that is C1 is included in G. At this point, we say that events contain both events. Generally, if event A occurs, event B must also occur. We refer to event B as containing event A or event A contained within event B, denoted as B containing A or A contained within B, as shown in the figure. Note that firstly, impossible events are referred to as empty sets, and secondly, any event contains impossible events. Specifically, if event B contains event A contains event B, that is, B contains A, and A contains B, we obtain that event A is equal to event B, denoted as A equals B. The second point is that D1 is a set consisting of 3 elements, 1, 2, and 3, with no more than 3 points. The event meaning E1 is equal to the number of points 1 or 2, so it is a set composed of 2 elements, 1 and 2. E is equal to 2, and the number of points 2 or 3 is a set composed of the elements 2 and 3. It can be observed that at least one of events E1 and E2 occurred, equivalent to event D1. The relationship between events can be represented in the form of a set, where sets 1 and 2 are combined with sets 2 and 3, resulting in sets 1, 2, and 3. This set of E1 and E2 equals D1. In this case, we call D1 the union event of event E1 and event E2. Generally, event A and event B have at least one sample point that occurs in such an event, either in event A or in event B. We refer to this event as a union event or composite event of event A and event B, denoted as A and B or A plus B. This event can be represented by the green and yellow areas in the diagram. Thirdly, point C2 is equal to point 2, which is the set composed of the element 2. E1 is equal to the set composed of elements 1 and 2 if the number of points is 1 or 2. E2 is equal to the set consisting of 2 or 3 elements, as the number of points is 2 or 3. It can be observed that event E1 and event E2 occur simultaneously, equivalent to event C2. The relationship between events is represented in the form of a set, where set 1 and 2 intersect and set 2 and 3 equals set 2. The intersection of E1 and E2 is equal to C2, and we refer to C2 as the intersection event of event E1 and event E2. In general, event A and event B occur simultaneously, and the sample points in such an event are both in event A and event B. We call such an event the intersection event of event A and event B, or the product event, denoted as a intersection B or AB. This event can be represented by the blue area in the figure. Fourth, represent event C3 as equal to point 3 and event C4 as equal to point 4 in the form of a set. They are the sets composed of elements C3 equal to 3 and C4 equal to 4. Obviously, event C3 and event C4 cannot occur simultaneously. To express this relationship in the form of a set, the intersection of set 3 and set 4 equals an empty set, that is, the intersection of C3 and C4 equals an empty set. At this point, we refer to events C3 and C4 as mutually exclusive. Generally, if event A and event B cannot occur simultaneously, meaning that a crossing B is an impossible event, that is, a crossing B equals an empty set, then event A and event B are mutually exclusive, or complementary and compatible. These two events can be illustrated as mutually exclusive. Its meaning is that event A and event B will not occur simultaneously in any event. Fifth, represent event F as an even number of points and event G as an odd number of points in the form of a set. They are respectively, the F set is a set composed of elements 2, 4, and 6, and the G set is a set composed of elements 1, 3, and 5. In any experiment, only one of events F and G can occur, and one of them must also occur. The relationship between events can be represented in the form of a set as sets 2, 4, and 6, with sets 1, 3, and 5 equal to sets 1, 2, 3, 4, 5, and 6. The set F and G are equal to the omega, and the set 2, 4, and 6 intersecting with the set 1, 3, and 5 is equal to the empty set. The intersection of F and G is equal to an empty set. In this case, we refer to event F and event G as opposing events, and events D1 and D2 also have this relationship. Generally, if event A and event B have only one occurrence in any experiment, that is, A and B are equal to omega, and A and B are equal to the empty set, then event A and event B are considered opposing events. And the opposing event of event A is called a bar. It can be represented by a diagram. Its meaning is that event A and event A bar have only one occurrence in any given event. In summary, the meaning and corresponding symbols of the relationship or operation of events are as follows. Let's look at the relationship or operation of events, including its meaning is that A causes B to occur, and we use symbols to represent that A is contained within B. And event, that means at least one of A and B happened. We use symbols to represent A and B or A plus B. Next, the meaning of intersection event or product event is that A and B occur simultaneously, so the symbol representation is a crossing B or AB. Mutual exclusion or incompatibility means that A and B cannot occur simultaneously. That symbol indicates that A intersecting B equals an empty set. The meaning of mutual opposition is that A and B have only one occurrence. The symbol represents that A to B are equal to the empty set, and A and B are equal to the omega. Similarly, we can define the sum and product events of multiple events. For example, for 3 events A, B, C, A and B and C, or A plus B plus C, if and only if at least one of A, B, and C occurs. A intersects B intersects C, or A, B, C occurs if and only if A, B, and C occur simultaneously. Below we will provide an example explanation. As shown in the figure, a parallel circuit is composed of 2 components, A and B. Each component may function normally or fail. Assuming event A is equal to component A being normal, and event B is equal to component B being normal. The first question is to write down the sample space representing the working state of 2 components. The second question is to represent events A, B and their opposing events in the form of sets. The third question is to represent event A in the form of a set, where event B intersects with event A and B, and explain their meanings and relationships. Let's take a look at the analysis. Note that the experiment is composed of the states of 2 components, A and B, so the sample points can be represented by arrays x1 and x2. In this way, when determining the sample points contained in events A and B, not only should the state of component A be considered, but also the state of component B. Next, let's take a look at the answer. The first question. If x1 and x2 represent the states of components A and B respectively, then x1 and x2 can be used to represent the state of this parallel circuit, with 1 indicating component normal and 0 indicating component failure. So the sample space is the omega set, and there are 4 elements inside 0, 0, 0, 1, 1, 0, 1, 1. Next, let's take a look at the second question. The second question is to represent events A, B, and their opposing events in the form of sets. So, according to the question, we can conclude that set A consists of 2 elements. One is 1, 0, and the other is 1, 1. The set B consists of 2 elements. One is 0 and 1, and the other is 1 and 1. So, a bar is naturally a set of elements 0, 0, and 0, 1, and B bar is a set of elements 0, 0, and 1, 0. Let's take a look at the third question again. Represent events A and B and events A bar and B bar in the form of sets and explain their meanings and relationships. So A and B are composed of 3 elements, namely 0 and 1, 1, 0 and 1, 1. A bar intersecting B bar is composed of 1 element, which is 0, 0. So, A and B indicate that the circuit is working properly, and a bar crossing B bar indicates that the circuit is not working properly. So, A and B intersect with a bar, and B bar is an opposing event. Finally, let's summarize the content of this lesson. Firstly, it includes the determination of equal relationships. The inclusion relationship of events is similar to that of collections. The essence of two events being equal is the same event, which occurs simultaneously or does not occur simultaneously. The first step in determining whether an event is mutually exclusive is to determine the results contained in each event. The second step is to determine if there is a result that would mean both events occurred. If so, then these two events are not mutually exclusive, otherwise they are mutually exclusive. The third knowledge point is the two steps of determining whether an event is contradictory. The first step is to determine the mutually exclusive event. The second step is to determine that one of the two events must occur, otherwise they will only be mutually exclusive but not contradictory. The fourth point is the relationship between events or the meaning of operations, as well as the corresponding symbol representation. That's all for today's content. Thank you.